In this module, we will explore the changes in thermodynamic state functions associated with the mixing of ideal gases. From the thermodynamic perspective, the change of thermodynamic state functions upon mixing of ideal gases is a simple but nevertheless important topic. Mixing of gases is very common in everyday life and in various practical applications, such as in gas reactors. We start our thermodynamic analysis by considering a system with different ideal gases in separate chambers. They are all at the same temperature T and pressure P, both kept constant by the surroundings. Each chamber contains a specific amount of pure gas, all subjected to the same external pressure, which causes their volumes to differ. This is our initial state. When the walls between the chambers are removed, the gases mix, and each gas is now characterized by its own partial pressure Pi. The total pressure and temperature in the combined chamber do not change upon mixing. Since these are ideal gases, they would remain the same even if they weren't externally controlled. Furthermore, the total pressure in the chamber P is the sum of the partial pressures of individual ideal gases Pi. The total amount of substance of gas in the chamber N is the sum of the amount of substance of each gas Ni. The mole fraction of each gas Xi is the ratio of its partial pressure Pi to the total pressure P, or the ratio of its amount of substance Ni to the total amount of substance N. This is our final mixed state. Before mixing, the chemical potential μI of each pure gas depends on temperature and pressure and is given by this expression. The total Gibbs energy of all the gases before mixing, when they are still in separate chambers G1, is the sum of the chemical potentials of each component, each multiplied by the number of moles of that component. It can be expressed as shown here. We see that the total Gibbs energy before mixing can be separated into two terms, one independent of the pressure and one that depends on the pressure P. After mixing, the chemical potential of each gas changes and can be expressed as shown here. Since there are no interactions between the molecules of an ideal gas, the chemical potential is not affected by the presence of other gases. The expression for the chemical potential of each gas remains the same, but now it contains its partial pressure in the combined chamber Pi. The partial pressure Pi of each gas is lower than the total pressure P, which results in a decrease in the chemical potential of each gas after mixing. This is a consequence of the dilution of the gas as it spreads throughout the entire volume of the combined chamber. The expression for the total Gibbs energy after mixing G2 is similar in form to the one for the Gibbs energy before mixing, and now it contains the partial pressures of each gas instead of the total pressure. The change in Gibbs energy during the mixing process delta mix G is the difference in the Gibbs energy before and after mixing. In this difference, the pressure-independent terms cancel out. Physically, this can be interpreted as an indication that the mixing is unaffected by the chemical nature of the gases involved. The terms involving the standard pressure also cancel out, and we can simplify the expression to R times T multiplied by the sum over I of Ni times the natural logarithm of the ratio of Pi to P. This expression shows how the change in Gibbs energy during mixing depends on the ratio of the partial pressure Pi of each gas to the total pressure P. In this expression, we replace the amount of substance of each gas Ni with N times Xi. The ratio of Pi to P equals Xi. After these substitutions, we obtain a simplified equation for the Gibbs energy change during mixing. N times R times T multiplied by the sum over I of Xi times the natural logarithm of Xi. As the mole fractions Xi are always less than 1, the natural logarithms of Xi are always negative. For any composition of the gas mixture, every term in the summation contributes negatively, and thus the overall value of delta mix G is always negative. We have shown that the mixing of ideal gases leads to a spontaneous decrease in Gibbs energy, confirming the idea that ideal gases mix spontaneously in any proportion. We can also calculate the change in entropy due to mixing of ideal gases. It is directly related to the change in Gibbs energy and is given by delta mix S is equal to the negative partial derivative of delta mix G with respect to temperature T at constant pressure P and the amount of substance of each component Ni. This is equal to negative N times R multiplied by the sum over I of Xi times the natural logarithm of Xi. Since the natural logarithms of Xi are negative for all components in the mixture, the negative sign in the equation indicates that the entropy of mixing is always positive for any composition of an ideal gas mixture. The enthalpy change accompanying the mixing of ideal gases can be calculated using the relation delta mix G equals delta mix H minus T times delta mix S. By substituting the expressions for delta mix G and delta mix S from previous equations, we obtain N times R times T multiplied by the sum over I of Xi times the natural logarithm of Xi equals delta mix H plus T times N times R times the sum over I of Xi times the natural logarithm of Xi. This shows that delta mix H equals 0. This result makes sense because the molecules of an ideal gas do not interact with each other. Therefore, there is no enthalpy change associated with the mixing of ideal gases. What is the driving force for the mixing of ideal gases? As we discussed earlier, the Gibbs energy change generally has two contributions, an enthalpic term and an entropic term. For ideal gases, the increase in entropy is the sole driving force behind the spontaneous mixing, and there is no enthalpy change.